Let's now look at a graph with some transformations in it of one of the cofunctions. So we've got secant of 3 secant of pi x. So what kind of transformations are we going to do? So first you of course want to graph the guide, just like we graphed the guide for plain old secant and cosecant. So let's write down our guide. You can write it as a function of x if you like. And you don't just want to use plain old cosine. Cosine goes with secant, of course. You want to do cosine with all these transformations in it. That version of cosine. So for the guide, let's write down what we know. We know that the amplitude of the guide is 3. The period of the guide, I think, also has a transformation. If you think back, what is the original period of cosine? It's going to be 2 pi. Divide by, if you've got a transformation, we do, it's going to be pi. That'll cancel out. So our new period of this wave is going to be 2 for the guide anyway. All right, so let's try to start graphing this guy. Okay, so my period is going to be 2. So it's going to take 2 to finish one wave, 2 more to finish another wave. We're going to be going up and down 3. I'll go back and do 3 waves. So cosine starts up, ends up, and in the middle it's down. Starts up, ends up, in the middle it's down. Ends up, in the middle it's down. Drawing my cosine wave. Something like that. Remember, neatness really counts, so make sure your graphs are nice and neat or you'll have issues finding things like the x-intercepts and stuff. For instance, on this guy, if the neater my graph is, the easier it's going to be for me to write down the asymptotes. Because remember, we're not graphing 3 cosine, that's just the guide. I wanted to graph 3 secant, so now I need to put in my asymptotes. So however you want to do it, I'm going to just do them right through the x-intercepts. Okay, so now if I drew my graph neatly, I should be able to figure those out without too much trouble. So the period was 2, that meant this was at 1, so this should be right in the middle if I drew it correctly, and between 0 and 1 is a half. So that is at 1/2, so that's -1/2. I'm not going to write x equals on all these, even though I should, because they're vertical lines. I'm just going to write those so that I don't get confused. So then this one is at 1.5, or 3/2. 2.5 or 5/2, 3.5 or 7/2. That's probably good enough. All right, so now I want to actually draw my actual secant pieces, which is right here, down here I've got a pseudo-parabola, so lots of pseudo-parabolas. Remember, there's really an infinite amount. We're only going to have a few because we decided to draw 3 cycles of the guide. Okay, so before we give up with this example, that's probably good enough. Something like that is what your homework should look like. Let's talk about the kinds of questions I might ask on a quiz or exam and stuff you should be able to answer. So if I were to tell you the domain of this function is all real numbers, -infinity to infinity, what would you say? I think you should tell me that that is not exactly correct. There's plenty of asymptotes here. Obviously, the domain doesn't include those asymptotes. The domain, in fact, would be, let's see, so we want to have everything except things like 1/2 and 3/2. So the domain would be all those x values except the x values of 1/2, 3/2, 5/2. We can write that down as everything x such that x is not equal to 1/2. And how far are these apart? I think they're 1 apart. So plus 1k, k being any integer. That's the true domain. So what if I asked you true or false? The range of this secant function is -infinity to -1, and then 1 to infinity, like the regular secant function. In that case, You should tell me again, not quite right, going for the right idea, but the range here is negative infinity up until -3 with a bracket, including -3, and then picking up again at 3 with a bracket up to infinity. What if I were to ask you or assert that there are an infinite number of x-intercepts for this secant function? Kind of looks like it, right? So my class today was really tempted to say yes. I think they were looking at the blue function, though. There were a couple people in the class that raised their hand and said, you know what, that's not right, Mr. McGee, because that's not what you're talking about when you're talking about the secant. That blue guy is just the guide. When you're talking about the secant, what you should really be focused on is these red pieces. You can, in fact, even go in, and it's kind of bad in terms of erasing, but you can go in and erase the guide function. The actual secant, if you put it in your calculator, for instance, you're going to just see these pseudo-parabolas, just those pieces. And clearly that never crosses the x-axis, so it's very false to say it has any x-intercepts, let alone an infinite amount. There's none for this particular function. What do you think? Would there be any secant function that would possibly have x-intercepts? Yeah, sure. If you have this function and you go like up by 4, then everything's going to be dragged up and some of them might start crossing in that case. All right, let's look at another function. We'll do one more function for this one. Let's look at tangent. Let's start out with just plain tangent of x. So what if we have f of x equals plain tangent of x? All right, so plain tangent of x. We could, of course, investigate this with the unit circle, but I'm just going to start drawing it. So to draw a tangent, I start by drawing on both sides of the origin. And these turn out to be, if you mess with your unit circle, pi over 2 and negative pi over 2. So if the pattern continues, you know what, we need to make this a little bigger. So if the pattern continues, where would the next asymptote be? Think about how wide this is. This is pi wide, right? So this should also be pi wide. So what's 1/2 plus 1? It's going to be 1.5 or 3/2. So then where would the next asymptote be? I think it's going to be 5/2. Okay, so there's a couple cycles of the tangent. So what's the function actually look like? It looks kind of like this. And it repeats, because altered functions are, of course, periodic. Okay, so there's 3 periods or 3 cycles of the tangent function. So let's talk about it a little bit. What is its period? Unlike sine and cosine, if you look at this graph and you think about how big the period is, that's 1 period, that's 1 period, that's 1 period. How far apart were my fingers in each case? Period's not 2 pi, it's just regular pi. What other notes should we have? The domain is going to be one of those infinite sets. We could write that the domain is all the x values such that x is not equal to, well, what can't we be? We can't be on that asymptote or that one or that one. So this time, you know what, let's just say 3 pi over 2 plus, how far apart are they? Pi k. K belonging to the integers. As long as we're not on one of those asymptotes, everywhere else is good. The range of this guy, think about the range. Guess I'll do it in a different color. The range of this guy is pretty simple, goes bottom to top, so negative infinity to infinity. The other, probably even perhaps most important thing to remember about tangent is that my class said, which other function does it resemble? Think about your library of functions for a second. Which other function does it resemble? My class quickly came up with x cubed in both hours. So it's just like x cubed except for 2 things, I think, mainly. The 2 differences are, number 1, x cubed doesn't repeat, it just happens once. And the other thing is, unlike pseudoparabola, very much like pseudoparabolas that are trapped in the asymptotes, these x cubed shapes, these snake shapes, as my first hour said, these wannabe snakes, they're trapped in these asymptotes as well. So they can't quite continue out forever. Remember, the domain is constricted. There are places it can't be. For x cubed, there's no such restriction. All right, And one other note that we're going to put here, probably the biggest one, I guess I'll do it in black here at the bottom, is think about how I started drawing tangent to begin with. For sine, remember we started by drawing the first point in the middle. For cosine, we started by drawing the first point up. For tangent, you want to start drawing the first two asymptotes. You want to do that on both sides of the origin. So I like to say that tangent straddles, because that tells me both sides the origin. Unless you've got some kind of phase shift which is going to move the tangent curve left or right, you're always going to start by straddling, and even when we do have those phase shifts, I'm going to start it that way, and you'll see those in more sophisticated graphs next week. Let's graph one transform tangent to wrap it up today. So let's pick another tangent function. Let's say we've got a tangent that is, I don't know, 4 tangent of, let's move it up as well. Let's go plus 1. Just move it up a little bit. We'll go 4 tangent of, let's see, I don't want to do just plain old x. Let's put in a 1/3. Okay, what would that graph look like? So we want to graph it. So let's talk about the period first. You might be asking, well, why didn't I start with amplitude? That's usually easiest, right? Well, look at your tangent graph over here. I don't think it's a wave. Only waves have an amplitude, which means, like, you know, the top and bottom of the wave. The range on this is negative infinity to infinity, so it doesn't have an amplitude. It doesn't make sense to talk about one if something's not a wave. Now that 4 is, of course, still going to stretch it. It's just going to make it steeper, and that's hard to draw, so don't worry about that too much on your graphs. Just to recognize that this is steeper. Let's write that down. The period, remember a second ago, the period wasn't 2 pi for tangent, it's pi. And we've got it divided by 1/3, so this guy's going to be finished with a wave, or no, it's not a wave, finished with a cycle in 3 pi if you do copy dot flip there. And then this guy is, of course, just going to be up by 1. All right, so tangent, we're going to take my advice. Tangent straddles, so we're going to go on both sides with our first set of asymptotes. This has to be 3 pi wide. So if it's 3 pi wide, how much each way do you have to go, you want to ask yourself? Well, 3 cut in half is 1.5. I'm going to write that as 3/2. If you want to write 1.5 pi and negative 1.5 pi, by all means, that's fine too. Put that about right here. So remember, we had to go 3 pi from there to there, so we're also going to go 3 pi from here to here. So what is 1.5 plus 3? So my class liked to go 4.5 pi, which is fine. There's a better way to write that, though. Think about how we've been counting in trigonometry. This is counting by halves, obviously. So if you've got 4, how many halves go into 4? Well, if you've got 4 pizzas and you cut them in half, you've got 8 pieces left. That means there's 8 halves here and 1 more half. That's going to be 9/2 pi, or 9 pi over 2. Okay, so now we've got to actually draw the tangent in there. So let's go ahead and do that. So we took care of the period. We need to remember to try to draw it a little bit steeper. And then we need to remember to draw it up 1. So instead of right here, it's going to go up 1 right there. And instead of in the middle, what's between 1.5 and 4.5? I think that's 3. Let's not draw it there. Let's draw it up 1. And we're going to draw it a little bit steeper. So a little bit steeper is going to go like this. I don't know if that's quite steep enough. It's probably more like this. Something like that gets the job done, though. I'll see you next time.